All right, today is January 21st, International Grandma's Day. Fanshawe College, CNTL3020, Controls 2, London, Ontario, 2026. All right, cool. How's that for a random introduction? All right, so we're going to warm up today with question number 7, random question. All right, pull it out of my hat. All right, so this one says, define the differences between hardwired logic and programmable logic. So you're welcome to join in, and well, if you feel like you want to join in on voice, go ahead, just pipe in. Any takers on that one? The differences between a hardwired logic and programmable logic. All right. I can see some cicadas chirping. Quiet on the front lines. Wow. Are you guys awake there? Can you hear me? Okay, we got a jolly crowd. Okay, there we go. Carbon here. Hardwired. It's a hardwired logic is fixed wired. So that's what Carbon says. Fixed software, where programmable is more flexible. So for the hardwired logic, and I get this thing covered here, and it's easy to change. So that's for the hardwired logic. Actually, I commend you for being brave and speaking up. However, that's actually the other way. All right, hardwired logic is there we go. But thank you for speaking up. If I had a candy, I'll throw it at you, but we're online here. Okay, so hardwired logic would be wiring. Okay, so you haven't studied the logic gates. However, I'm introducing you slowly to that type of concept of logic and logic gates. Boolean type of a logic, that's what it's called. So there would be wiring an AND gate, maybe with another OR gate, and maybe with another inverter, which is a NOT gate. I don't think I have shown you that one. An inverter is basically if you have, it just has one input and one output. And when you put logic 0 on the input, you get logic 1 on the output. And the other way, if you put logic 1 on the input, you get logic 0 on the output. So if you get bunch of those gates, those logic devices, and wire them in a certain way so it performs a certain task. For example, if you have a circular saw on the production line, those saws, it's a it does have things that are spinning, and those blades are sharp. So you just want to make sure that you introduce as many safety precautions as you can. So let's say, for example, if you press the foot pedal and you turn the on switch, so if you just operate the on switch, that thing turns on and the blade spins. So this would be 2 inputs producing one sort of an output. So if you stand on the foot pedal for safety measures and turn on the on switch, operate the on switch, both of them would be logic 1 by the convention that we assume to be, because, well, I'll get back to that. Then one and the other will give you the result of the blade spinning. If one of them becomes logic 0, which maybe if you would step off the foot pedal, then you would have logic 0 on one of the on the inputs, and you do not have both logic 1s, then the blade stops. So this would be a hardwired logic because there is no software needed for that. You could do this with the software, but you can do this thing with the hard wires. Wire those things, the logic, in a way that it operates a certain way. It is hard to change if you have a larger production line set up to do multiple tasks, some of them complex one way or the other. And then if you have to change the whole thing, you have to basically disassemble all the relays, all the logic gates and everything else, all the equipment, and you have to rewire that in a different way. So if it's sometime during maybe 1970s, there will be a huge car assembly production line, and if somebody wanted to do this to a different, somebody wanted to change something, then the production line had to be stopped, so things would have to be rewired. Okay, so that's be hardwired logic. And when it comes to programmable logic, right here, then well, you could get some common modules, and maybe you have to move something one way or move something the other way, maybe install another module or anything like that. But when it comes to the operation logic of this whole what if routine, then you can fix it with the software. And if you need to make something go longer, or maybe something push further, or maybe there's another condition you want to introduce. If something happens, then do something else, and you can do this thing with programming, and that thing often could be done overnight or over the weekend. All right, so let's see here what the survey says. Hardwired logic uses physical wiring and relays for control, providing reliability but limited flexibility. So what about the reliability? Well, there is no software to go wrong. There is no virus that can sneak into the wires, unless there's some big rodent, a mouse or a squirrel just bites into the wires, so I suppose. Programmable logic uses software-based controllers like PLCs, programmable logic controls, allowing the adaptability and scalability for automation. What else does it say here? Evolution in control systems. Transitioning from hardwired to programmable logic has revolutionized industrial control systems with enhanced flexibility. Okay, so that's enough with the questions for today. That was a good warm-up. What else do we have in the store? Okay. Remember that presentation? I think it was last week. No, last week we were doing the other ones 2 weeks ago. We're going to solve a couple of problems here. All right, so this is about the conservation of volume. It's just a reminder of a couple of, I'm just turning a couple of slides back to where we started. And thank you, Corbin, by the way. All right. All right, so volume displacement, conservation of volume. All right, before I do that, I'm going to bring up my board. Where's my board? Here's my board. All right, let's say we have a couple of cylinders, and I'm just going to do a 2D type of a drawing here. We have a smaller cylinder. Where do we get all those slides? These slides should be already posted. So look at the content under the student content. If not, let me know, because maybe some switches were not turned on to make it visible for you. And that's a good question. Thank you for asking that, because that's going to make me check after this presentation, just to make sure that all those slides. And I'm also going to put together all the notes from today's in-person lectures that we saw each other for 2 hours. All right, let's say there's a one cylinder and there's some sort of a connecting line hydraulic line or pneumatic line, so this either contains air or some sort of a fluid, and we have that thing being connected to a bigger cylinder, and let's say there's certain amount of oil. So let's consider that a hydraulic system, and there's also a certain amount of fluid here. Let's make it, kind of a straight line here, and we have a piston and a plunger, and we're going to push this down. Now with this, if we push this plunger here certain amount of distance from here to here, we're going to displace that amount of fluid in this small cylinder. So it's going to contain a certain amount of, let's say, milliliters, or maybe half a cup if you're a cook or a chef. All right, so we're going to displace a certain amount of volume. That volume has to go somewhere, because if we're dealing with a closed system, then it's going to go into this, and this volume that is going to disappear from this cylinder, it's going to appear in this cylinder. So this volume and that volume are going to be equal. The volume lost here is going to equal the volume gained here. However, if this is a smaller cylinder, we have to push this one so far, and when that volume appears on the bigger cylinder, the same volume, then it's not going to push that, whatever, maybe there's another piston here, all right, with a rod. It is going to push it up, but not as much, not as far of a distance than this one here, because we have bigger area here, and that volume is going to disperse in a larger area. So that's what we are dealing with here. Volume. And what is volume? Volume is area over a distance, or area spread over a distance. So if we have certain area of a piston or a cylinder, and that cylinder is going to be displaced a certain distance, that volume displaced in one cylinder is going to equal the volume displaced in the other cylinder, even if those areas, if the things are different size here. So if you have a bigger area, then the distance is going to be smaller in order to keep that equal sign. Right? So volume of the fluid displaced goes by the V designation, and here is area 1 at the first point, area 2 of the second point here. Here's the first point, here's the second point, all right? And we have the distances. Now, what else did I say here? Assuming the fluid cannot be compressed. That's a big assumption that has to be met, big condition, because, well, it works with hydraulics, and it does also work with pneumatics. However, just keep in mind that pneumatics uses air or gases, and gases are compressible. Hydraulics uses fluids, mostly oil. It can be water, yes it can, but we're dealing with mostly oil, and that, in comparison to the pneumatics, that medium that is in those pipes that we're moving is considered incompressible. So we have more control with hydraulics as far as the distance displaced and the equality of speeds, I would say. All right? Because what's happening with the air when it's acted up on in a cylinder, yes, it's going to compress a little bit, and it's going to decompress again, but we're getting some sort of what we call a spongy type of effect, right? Or springy type of effect. All right, so assuming the fluids cannot be compressed, so we're dealing with oil or hydraulics in this case, the volume of fluid pushed through the wider section must equal to the volume of the fluid pushed through the narrower section in the same system. This principle is often used alongside the Pascals principle in hydraulic systems to understand how much the piston is going to move. Right? Pascal's law, the pressure is equal everywhere. All right. And here's the famous last picture here of a car jack. What do we have here? It's a kind of a bad design, right? Because you push on that handle, this thing goes up, right? So, okay. But this is it's just a conceptual type of a drawing. So we have a certain size of a piston right here, and certain size of the cylinder and cylinder. There's a piston and whatever else. If you pump this one, you move the handle a certain way, and you have to move it more distance for this thing to come up, less distance. What do we gain from that? Why would anybody want to do that? Well, to get the mechanical advantage of the power that can be done by the multiplication factor. And we're going to tackle that as we go along. So in this case here, you just get one movement of the handle, you push this thing down, and that thing pushes up. So if you push it a long distance, this thing is going to push very short distance, so not a very useful. It's almost there. We're almost there, right? But this just shows this thing just shows the concept. Shows us the concept. Here's how the more realistic than the previous one jack here. What do we have as far as the hydraulic system? Here's our pump unit. That's the handle that pushes things. Now we can pump it instead of just moving it. Over here we got, believe it or not, this is supposed to be check valves. One-way control, one-way flow control, check valves. Remember the ping pong balls analogy that we used in the one-way control valve with the pneumatics when we were adjusting the airflow? So it's a similar idea. What do we have here? We have a blockage, and this suggests there's a spring. It's a spring-loaded device. So that thing here is closed by default, and so is this if nothing acts on it. So with the reservoir, and there's no pressure in the reservoir, you just can top this thing up. Did you ever have to top up your brake fluid in your car? Well, here's your reservoir. Right? That's what, and there's no pressure. You can just unscrew this top and just take a look at it. Right? There's no pressure here, but there's just enough fluid for us to work with. How does this one work? All right, on the downstroke here, by the way these check valves are installed, what is going to happen? Introduce a pressure here. The pressure is going to disperse in all the directions. This, the way it's installed, this check valve is going to block the fluid from going that way, traveling that way. But look at this one here. It's installed the same way. Looks like it's the same way, but those two with the downstroke, they act different, because this one is going to push this thing, this blockage out. The check valve is going to open, and the fluid is going to flow this way here, creating a pressure in the bigger cylinder. So you can do a downstroke and you can just pump it. You're going to displace a certain amount of volume, and as soon as you stop applying pressure, that check valve is going to close, keeping that from returning, keeping all the medium from returning that way. But on upstroke, when you move the handle up, you're creating negative pressure going upwards. So the negative pressure is going to open this check valve, is going to intake some of the fluid from the reservoir. So you could press it down again and push it this way. So that's how you get the pumping action here, and that's how the car jack, for example, works. Cool idea, if you ask me. All right. So we have a little problem to solve here. Practice problem. Hydraulic service lift, so hydraulic jack, car jack here. A car mechanic uses hydraulic lift to raise a vehicle. This lift contains a small input piston and a large output piston connected to an connected by an incompressible fluid. So there's incompressible fluid here. All right. The input piston has a cross section of 5 square centimeters. So here's the area 1 centimeters squared. And the output piston, which supports the car, has a cross section of 100 square centimeters. All right, question. What's the question here? If a mechanic pushes down the input piston 20 centimeters, so that thing goes down 20 centimeters, how many centimeters will the other piston go up? All right. From just by looking at it, we can tell that it's going to take a longer distance to accomplish shorter distance here. But we get the mechanical advantage of the force here. Force be with you. All right. So solution here, we got that volume, the formula for the volume displaced. We have the areas, we have the distance, and we're going to have the volume displaced, and so on. So, well, what do we have? We have the area of one. We have the area of the other one. So we got this one, and then we got this guy here. Now, we have the distance of the first one that moves 20 centimeters. So this is going to be 20 centimeters here. And all we have to do is derive that. So we can just scratch that, so just to make things easier for us. We just have to solve for D2, because that's what we want to know. That's going to be the D2, and it's a simple calculation. Just have to remember that you need to equalize the units. So if one unit, if one distance is given to you in meters and the other one is in feet or something, you gotta bring them to the same sort of thing to make this thing make sense. In this case, we have the area in centimeters squared. The other one is also in centimeters squared. Just pay attention to that. And there's a simple calculation here. So in this case, we're going to move 1 centimeter here. You can, you should be able to download the thing. So if you look at it long enough, or just practice this, you're going to get 1 centimeter. So 20 centimeters here gives you 1 centimeter here. What would be the multiplication factor on that, or the multiplier? Well, the mechanical advantage, or the multiplier in this case, is 20 to 1. Keep that in mind. Okay. By the way, I'm going to start introducing quizzes for you. Quizzes are going to be online, and you can use whatever resources you can. It's for you to practice. It's still you're going to be rewarded with certain little amount of marks because of the easiness of things. It's online at your own convenience. However, the tests are going to be done in person. So I'm going to allow, or I'm going to encourage you actually, to all the formulas I'm giving you, just make a list of all the formulas and make sure you understand what they refer to, how to use them, because on the tests I'm going to let you in with the so-called crib sheet, because we don't want to call it a cheat sheet because it just doesn't sound good. And you can have all the formulas with you, so you can solve the problem. It's just knowing which formula to use and how to apply that formula. Okay. All right. We already went through this one here, but let's just quickly go over that, how we're doing with time. Yeah, okay. Hydraulics and pneumatics differences. Hydraulics versus pneumatics. Compressibility. Hydraulics is incompressible. You get immediate response. Pneumatics, you get compressible gas, so you get spongy or delayed reactions. Pressure levels. Look at that. With hydraulics, you get. Let's look at the pneumatics first. It's usually lower pressure. It will be 80 to 150 psi, which is pounds per square inch. And look at that here. Much higher pressure that we're dealing with hydraulics, up to 10,000 psi. Look at that. That's not even close to each other. Precision, you get high precision with hydraulics. You get fast response. Much faster response, but not as precise, not as controllable as far as the precision. So it's either on and off, it's either full extent or full retraction of a cylinder, and over here you can extend the cylinder so much and stop. All right. Components needs a reservoir tank for the hydraulics, and components vents used. All right, vents that can this one says vents that can take the used air into the atmosphere. All right. Okay, cool. All right. Let's see a couple more problems here. Problem 1, problem 2, and a problem 3. So I just listed them, and I'm just going to have the first problem here. All right. Let's see what else do we have here. A hydraulic jack has an input piston with the area of 0.002 meters squared. Okay. And the output, much bigger, 0.1 meter squared. All right. Let's just stop and do something here for kicks. I'm going to bring up a calculator. These are the same units, meter squared, so we're good. Let's go 0.1, divide that by 0.002. 0.002. Yeah, that gives us 50. 50, right? Because that gives us 50 here. Remember I was talking to you about the multiplier? Or the multiplication factor. Nice thing to keep in mind. All right. All right. So let's see here. If you apply 200 newtons to the input piston, then there are two questions here. What is the pressure generated in the system? And then question number 2. Is what is the maximum weight or force that the jack can lift? All right, what do we have here? Answer number 1. The pressure is defined as force per unit area. So we have the formula here. P equals force, pressure equals force times area. All right, we have the area, we have both areas. We're trying to find out the pressure. All right, we have both areas here. Just apply the numbers, and we just have to make sure that whether we are working with the imperial system or whether we're working with the metric system, just have to pay attention to the units. Always pay attention to the units, which means write them down along the way as much as you can. So So the pressure in the whole system, because it's a closed system, and by Pascal's law, we know that once we have a pressure in a closed system, the pressure is the same at every single little point of the closed system. So the main pressure, the pressure is force, we have the 200 newtons, and the units we're trying to accomplish is in the metric here, so, well, why not newtons per meter squared? So that would be the metric type of other than PSI, pounds per square inch. So since we're working with the newtons, so doing with the metric system, and we have things in meters squared, so why not stay with the metric system? So are we going to get at the end newtons per meter squared? Because if at the end if we look at the units and at the end result we get some weird unit that you get maybe degrees Celsius, then something went wrong somewhere along the way, right? So keep the units all along the way. And I do an extra step. I put all the units in square brackets. You don't have to, but it helps. So 200 newtons by 0.02 meters squared, because there is a force, and the area, the input, just have to make sure that you get the same force applying at the same area there, and that is going to give us a 100,000 newtons per meter squared. Okay, and just so we know, 1 Pascal equals 1 Newton per meter squared. I'm throwing this thing at you here. All right. So we can just say that the pressure generated in the system is 100,000 pascals, because by this relationship right here. 100,000 pascals equals to 100 kilopascals. And just so we know, 100 kilopascals is the pressure, the air pressure level on our planet if you're standing at the sea level. And sometimes the weather report is going to give you, okay, tomorrow we're going to have the pressure go up to 102 kilopascals. That's going to be a good day. When the pressure goes down, then, it rains and all that stuff. Some people get headaches. All right, so here is the first answer to the first question here. What is the second question? What's the maximum weight or force? We can use, in this case, we can use these two exchangeably, that the jack can lift. How heavy of a load can we lift with this jack, with these given right here? All right, according to Pascal's law, the pressure is the same in both input and the output pistons, because Pascal's law says that once you have a closed system, you have the pressure equal everywhere. So that's very good information for us to have. All right, which means that the pressure in one spot is also equal to the pressure in the other spot. All right, so the force on the output piston, F out, is calculated by multiplying this pressure by the output piston area. Yeah. So the system pressure that we just accomplished by this calculation, it's 100 kilopascals, so we know that. The output area equals 0.1 meters squared. So the force, the maximum force, because that's the pressure we get to, that's the force we get to deal with. So that force is going to lift what? The force out, in this case, is the main pressure, which is the same. We already have that. Pressure is the same everywhere, so we can use that information to our advantage. And force equals pressure times area. Ooh, look at that, same formula here. Eh? So we have 100,000 newtons per meter squared times the area, the other area, and that's going to give us 10,000 newtons. If we, well, I always encourage you to look at the units here. So we have newtons. Let me just get a pen here. Okay, what about this? So we have newtons per meter squared times meter squared. I want to see the units. So meter squared is, we can rewrite that, meter squared over 1. All right, look at that. These cancel. We are left with newtons, which means our calculation checks. We get the right unit. That's a double check to make sure that our calculation is correct. Okay, so and then give us the answer. The maximum weight force the jack can lift is 10,000 newtons. Let's see something here. We have 200 newtons applied, and we get 10,000 newtons on the bigger cylinder, except we're not going to move it as far, but we can just do more strokes and we can accomplish lifting up the car. Let's see one more thing here. Get a pen. We have 10,000 newtons. 10,000 over this right here, 200 newtons. I'm just going to write the magnitudes. Let's get the calculatable thingy device. I'm pretty sure you're guessing pretty correctly what's going to happen. 10,000 divided by 200. Oh, look! It's 50. Huh. Isn't that cool? Well, what else can we see here? Remember this formula? Pressure equals force over the area. And in both cylinders, we have force. Oh, well, we have the same pressure in both cylinders, remember? So this equals to pressure. See that here? Yeah, pressure, force over the area right here. And because pressure is everywhere the same by the Pascal's law, then we know that this pressure, which is from this formula, equals to the pressure there, and there's an equal sign here. So once we get the mechanical advantage or the multiplication factor, we could use that to our advantage again. Because this equation you can rewrite any way you want. This one here can be rewritten as, let's say, F2 over F1, and we're going to have same as A2 over A1 this fraction, if you apply the numbers, is going to give us a certain number. This fraction is going to give us a different number than that fraction. However, if we arrange that, we have an equal sign here, and that's all we care about in this case. Once we get the multiplication factor right here, then that can save us a lot of time, because once we have that, in many cases, we don't have to go through all kinds of calculation steps. We just, okay, so in this case, we have 200 newtons. And once we establish that multiplication factor, just multiply by 50, and here you go. You got the weight that can be lifted. How are we doing with time? 43 here. I would encourage you, because you can download this whole thing, I would encourage you to go and analyze this problem here, and analyze this problem here. All right. Because I'm going to ask you some of that on the test. I'm going to ask you to solve some of these things, and I might be a little bad guy, because I might give you some units, some numbers in different units. So you're going to have to pay attention to the units as well. All right, so this is it for today's class, because I gotta, once I stop, this video is going to start doing itself, putting itself into one piece, and I have the same class to repeat at 7 o'clock, which is about less than 10, about more than 10 minutes here. So that's it for today, and I'm going to see some of you tomorrow. Tomorrow is what? What's today? Wednesday? Today's Wednesday, so Thursday I'm going to see all the rest of you in the lab. So Ms. Tomaszewski said that the lab went quite smoothly, so I would expect that same thing. We're going to have a lot of headroom when it comes to the time. Most of us finished an hour, less than an hour and a half, so we should be okay with the 2-hour window frame for that. Cool. Have a wonderful rest of the week, and I'll see you when I see you. Thank you so much for your attention. Okay, I always have problems with these. Here we go. Mr. Zoom, make it more convenient. Okay, thank you. Goodbye.